Rianzu, you found the form I sent it to you? The form I sent to you, you have it, right? The email? You proceed with that. Get signature, give it to the dean's office, okay? All right. So I put this thing on record. I was talking something with the students, those who are watching the video. I would like to repeat it again, which is the final exam is take home. I'm gonna give it to you on Friday, and Friday there won't be any class. No class on Friday. Not this Friday. No class on week. Let me put it this way. That way there won't be any confusion. Week 14. Week 14, lecture 3. There won't be any week 14, lecture 3, Friday, and I'd like to put the date so there won't be any confusion as well. The date would be, what is the date for the last class? So May 1st, 26. Okay, but I will upload video lecture. Okay, all right, so that's pretty much it, and it's take home only. Final exam take home only, and the syllabus is chapter 15 and 16. It's mostly chapter 15 I'm gonna cover, and 16, right? 16 I haven't studied it. I just have two problems I'm gonna cover. So that's pretty much it. And the agenda for today's class is very simple. I have two problems. Let me see if I can show it to you. So this is one of the problems. There's another problem that I would like to solve it, and there is a new homework at the last one uploaded in Brightspace. Take a look. Homework number 11. So homework number 11 due on next week. The last homework. There won't be any more homework. Okay. So please submit it. And homework 10. I saw the deadline was 17th of April. Only 3 students submitted it. I'm gonna give you 2 more days. If I don't see you didn't submit it, I won't be giving any grade. Okay, putting it in record. The extra 2 days I'm giving. I'm not supposed to give any deadline, any extension or anything. Just be serious, because homework 11 is already there. If you don't submit homework 10, I mean, you can't just submit all of it at the last moment. Okay, you have to be on time with everything. Okay, come back here. So these are my agenda as I was talking these two math problem. I'd like to talk a little bit with this theory as well. Okay, so we are talking about impact, and in last class math problem or last few classes, what we are seeing basically two theorem. One is the momentum, linear momentum conservation. Other one is the impact, right, and momentum conservation. Those two equations we're constantly solving, right? When we're talking about the linear momentum, it's just coming along a straight line, right? What if we'd like to know, you guys all played tennis ball, right? You have seen the ball like tennis ball, right? So, so how to know when you're gonna buy a tennis ball that the quality of the ball is good? There must be some criteria that they use, right? So the criteria is like when it get impact, it come back to a different angle, right? So the initial velocity and the final velocity, based on that, we can kind of the velocities kind of dictate like how good is the ball, like how elastic is the ball. Okay, if it's more elastic, then it will gonna completely regain, almost completely regain its velocity, that initial striking velocity, right? When it is not, then what may happen? You have seen the slime, right? What happens? So if you're gonna push the slime somewhere, it just stick over there. It didn't come back, right? So that's too much of plastic. You know what I'm saying? So two opposite end example I was trying to portray. One is like too much elastic, ball coming back, and the other is kind of trying to stick together, right? So there is a parameter that dictates that. I'm sorry, you didn't see any of this thing, right? So there's a parameter that dictate that, right? This is the ball example that I was talking. And by the way, I did check in Brightspace. I did upload everything. All the materials are in Brightspace. Chapter 15, chapter 16, all the materials, whatever you're seeing here, okay? So that's the example that I was saying, just applications. Please read through that. Because we have like two math problems agenda wise, so quite a bit of agenda. I'd like to skip a little bit. But this is where I'd like to focus on. Okay, you see, so far we see the line of impact is along the same axis. What if we have an angle impact, right? As you can see here, two balls track together, and once they track together, they'll come and they have a path goes like this way, and another one is going to go like this way, right? Something like that. So if you have an angle of attack, then how are we going to analyze that? They call oblique impact. So that something is also explained here. But the linear impact one, this is the equation that we used in last class. Okay, conservation of linear momentum. If you remember, you guys remember the two velocities and masses summation before the impact and after the impact could be written like this way. Okay, so this one is so important. This one is called, let me try to highlight, coefficient of restitution, E. Okay, and what is that? It's the ratio of relative velocity after the impact and relative velocity before the impact. It's the ratio of that. When I said relative velocities, you see the difference of these two velocities. Which velocities again? See, when those things attack with each other, this could be a good example. Say like this is A and B attacking with each other, right? So before the impact means the velocity before, so it would be like VV VB1 minus VA1. That's the before the impact. And after the impact, what will happen? See, BV2 and 1 and 2 can be explained by before and after the impact, right? And BB2 minus VA2. You understand? So these are the two ratio I was talking. If you know this two ratio, before and after relative velocities, if you can get those ratio and divide it by each other, you can find the value of the E. And E is again what? That's called coefficient of restitution. You should be writing it. Restitution. Again, that is E. Second, E is what? VV2 minus VA2, VV1 minus VA1. Okay? And what we're going to do with this A and why do you need it? That's the question, right? If the value of E is 1, that means is it more elastic or more plastic? Elastic. Thank you. That means like it's completely regaining the velocity almost as if like. Does it make sense? Anybody? So like, when two of them are attacking, like two projectiles coming together or two balls or whatever objects coming together, having a collision, right? Just before the collision, they have some speed, right? When they're coming together, and after the impact, they're going to go back to a certain speed. So as if like you have whatever the speed it comes together, the same speed is going back, right? So that's like elastic. Does it make sense? So it's like it's elastic, right? And if it comes here and it stays, that means it's plastic. Does it make sense? So that means stays means no velocity is getting back. So the top would be 0. So when the value of E, if it is almost 0, close to 0, it will be very close to E. E value is very close to 0 or 1. So 0, very close to 0. So then it means it's plastic. And when the value of E or the top and bottom ratios are almost same, then it's called elastic, right? So elastic and plastic, those two things. All right, I don't have anything more here. Okay, if you take the notes, let me know. I'll just move on. This is all the main theory here. Then conservation of linear momentum. What is the coefficient of restitution? Those are the things important. We'll be doing it here in math. Today is Monday. Is it Monday? Yes, Monday. Week 13, day 1, Monday. Week 13, day 2, Wednesday. I'll be finishing up this chapter. And I don't need more than 2 days for chapter 16. I won't be covering too much, okay? And you would be ready for final exam. As I was saying, I almost have, these are the explanation. Elastic impact, plastic impact, as the E value is 1, E value is 0, what happened is exactly what I was saying, right? Take a look on it there. Coefficient of restitution, and there are some examples with the values, as you can see here. Steel to steel, The impact values of E should be what you are expecting, wood to wood, right? Lead on lead, glass on glass. Glass on glass is almost like no deformation. Glass is almost like a solid, rigid material, right? Wood does have some deformation depending on what kind of wood you are using. If you are using pine wood, you can possibly have a little bit less of the value, right? You know that, right? Whereas if you are dealing with, I don't know, birch tree, you know, birch tree is very, very hard. Okay, possibly the value would be a little high. Impact of energy, you know about this. There's some more equation, and just it's like for oblique impact, similar equations. Okay, um, in x direction and y direction, you'll have two different values. You're gonna come up. You obviously understand, right? In oblique impact, you know, right? When something is going at an angle, right? It does have an x and y component. So basically, it just says that here. Okay, we'll have two different equations. We'll do a math on that. So at that point, not today. At that point, we'll have more idea about it. Okay. For now, I guess I can kind of skip it. The theory, right? So two math problems that I have. Let's go one by one. Take a look on the problem. All right. So ready? Let's start with this problem. Okay, so this is a relative velocity problem, by the way. So a free rolling ramp has a mass of 40 kg, this mass that they're talking. Okay, a 10 kg crate, oh, this is, sorry, what I'm saying. This is the 40 kg and this 10 kg crate, I didn't quite see the 10 kg thing. So 10 kg crate, so the crate is on the top, the free rolling ramp is 40 kg. Okay, so this is the crate. So this is 3.5 meter down to the ramp B. So the ramp is like 3.5 meter. Assume that the ramp is smooth and neglect the mass of the wheel. So this wheel mass you are neglecting. You have to find the ramp speed when the crate reaches B. Okay, so this ramp speed when the crate reaches B. What really happened here? To understand, you have to first zoom the axis x and y this way. Okay, and then if you know this angle, you need to find some dimension. Okay, you need to find this two dimension. So where this height h is 3.5. By the way, this is 3.5, the hypotenuse. 3.5 sine 30. Okay, I shouldn't draw this thing exactly like that. It should be like this. All right, so as if like you have a right triangle here. Okay, so how are you going to solve it? To find the speed when the crate reaches at B. So you have to find B, C, R. okay, and if you're gonna assume the crate velocity is bc, you see c is referring here crate, okay, r is the ramp, okay, so you have to find the ramp speed, okay, when the crate reaches at b. So you have to find the relative speed. Everybody understand? Arlene, you got it? So this c and r, c is for crate, r is for ramp, okay. You have to find the ramp speed relative to the crate. Got it? So the crate is moving on the ramp, right? When the crate comes to point B, you got to find the speed of the ramp because the ramp is going to push back, right? Okay. All right. So that's the thing. Okay. So let's draw a free body diagram with this movement. So first of all, we have this movement of the crate, which is BC along this direction. Okay. And the component of the BCs are, you have BCX and BCY. So that is so straightforward, right? Because the BC has two components in x and y direction, right? So then if you're gonna draw a perpendicular line, right? And this angle is 30 because this angle is 30 here. Everybody remember that? So let me try to draw it from the triangle. So this is the ramp, right? And this angle is 30. And if you're gonna draw a perpendicular line and x and y axis, right? So say like this is x and y axis, understand? We have done it so many times, right, already? Listen, remember that, the 30-degree angles? Everybody remember this? That's from geometry, okay? I did derive it several times already in this class. Dylan, you got it? All right, so that's the reason I had this 30-degree angle over there, okay? So try to understand. So what we're trying to find, remember, the ramp velocity with respect to the crate. C and R refers to ramp and crate, right? C means crate, R means ramp. All right. So this is what you got to do. Let's start with the solution. So from conservation of momentum, so the ramp mass multiplied the initial velocity of the ramp plus the crate mass, which is 10 kg, multiplied the initial velocity of the crate. I refers to initial, okay, before the crate comes to B or impact, okay, and so these are the initial velocities. Let me write it here this way. These are the initial both ramp and crate. Now here's the thing, initially both of them are not moving. They start from ground zero, right, with no movement. So these are the value of 0. So the whole thing is 0, the left side. On the right side you have mr is the ramp mass, vr plus mc vc. Now what are those? The final velocities and mass of mr and mc. So you can write them like, final velocities and masses of ramp and creds. All right, now you can further write it like in left side it's 0 because the velocity is 0 for both cases. And in right side you have only the masses are known, not the velocities. So you'd be writing like 40 multiplied VR and 10 multiplied VC. All right. So when you are finding the velocities, see, here's the thing: where the crate is moving and where the ramp is moving. The crate has a movement of 30-degree inclination, right? However, the ramp has a movement of which direction? X and Y. Only the X direction, right? We got it? So the velocity VR, you can write VRX, doesn't matter because it's just one VR because the ramp is moving only horizontally, right? In X direction. So I'm not putting in subscript, but when I'm writing the VC, see it does have two components because it's coming to a ramp, right? Angle. So I'll be only considering the X direction velocity. Does it make sense? Now you may argue what happened with the y direction velocity and the momentum for the y direction velocity because it's still moving. So there's a normal force, right? That balance it out. Makes sense? So it's the VCX, right? So VCX and VCY. And where do you see it? It's very straightforward. You're seeing it here. Let me try to point it out. See VCX. And you may see it further down here if you wish. So this does have two components, right? This is your VCX, this is your VCY. If you'd like to understand more, right, in the sketch itself. All right, so then what? Then you can rewrite the whole thing as like VCX equal minus 4 VR. Now, how do I get it? I'm just rearranging things, right? Taking this 10, I don't know, maybe. Sometimes I lost a student if I do that. So I don't want to do that. So let me do it this way. 10 VCX equal minus 40 VR. I wish I didn't lose it because this minus is, I should have put the minus here, plus here, and then minus this, plus is, okay? Understand? So eventually you have minus here. So this 0, 0 is going to cancel out, right? So BCX, that's the thing I wrote, equal to minus 4 VR, right? And I'd like to put it as a equation number 1. This is my first equation. Now, if you remember from exam 1, right, back on those relative velocities days, so on this relative velocity days, we know the crate velocity can be written as the ramp velocity plus the crate velocity with respect to ramp. Because remember that is a velocity triangle from first exam 1. Okay, if not, then just please review it one more time. Where did you get it? Again, very straightforward. I do have this velocity triangle. I do have this thing here, right? The velocities are drawn here in different angles. Okay, so then I don't know if you recall. So you have, when you're going to write this equation, this is a vector equation, right? So you can put an arrow on the top or no arrow, doesn't matter. I mean, write it in bold letter, arrow, or sometimes they put a dot on the top of those. Different way people put the vector, right? But bottom line, it does have these two different directions, right? X and Y direction. I was talking about it, right? Because the ramp, that goes only X direction. The crate, however, goes in two different directions. So it must needs to be counted as a vector. So if you want to do it as a vector and take only the X component, so you should be writing VCX I okay. First, I'm going to write both X and Y component, okay? And then I'm going to separate them, just for your understanding. So can anybody tell me in the right side, why did I put a negative here before the BCY? Because the crate is moving from A to B, which is which direction in Y? Negative Y direction. Everyone got it? Do you understand why I put a negative? The crate is moving down, right? Negative Y direction. All right, so then on the right side, I should be writing minus VRI. Can anybody tell me why I have this negative VR? You guys remember Newton's third law? Everything has an equal and opposite reaction. So think this way, Ali. If something is moving, okay, this way, it is going to push something on the back side, right? Does it make sense? So the crab is moving positive x direction. The ram should be going opposite to the crab. Does it make sense? Right? As if like if you're trying to walk in a roller, that thing will gonna go on the back, right? You're gonna go on the front. That's the thing I was trying to explain. Okay, so that's why you have a negative over there. And this CR is like very straightforward. It does have two components as well. Take a look on this VCR. You see, there's this 30-degree angle I was explaining before. It has this cos 30 and sin 30 component. So you should be writing it this way: cos 30 I minus sin 30 j. Again, it's very straightforward because you see it's going down, so that's why you have a negative j direction. And then what you'll be doing next is like as if like you are separating the I component only, right? Okay, and j components again the same way. So you have two equations, obviously, x direction and y direction. You can write it this way: x direction and y direction, right? The same equation you are writing. So the x direction one would be what? BCX equal minus VR plus BCR cos 30. So that's say like equation number 2. And then VCY, again this is the velocity for the crate in y direction, minus VCR sine 30. That's the equation number 3. Okay, so what you're trying to find here, you're trying to find at least one unknown. So like VCY you'd like to find first, okay, in terms of VR. So what we're gonna be doing with that? Remember, our goal is to find the ram velocity when the cart reaches at B. So VR. Okay, we talk about this VCR, the crate velocity with respect to the ram. We see the force triangle. We wrote the vector equation for the force triangle. We divide into I and j component, means x and y direction components, right? We came up with the two equations. We had the conservation of momentum, one equation as well, because you have like three unknowns, right? You have like the VCX, you have this VCY, okay, you have this VCR. So that's the challenge, right? So what you're gonna do, you gotta get a relationship with VCY and VR, so you can apply it in the energy conservation equation, and you can get the value of the VR. Again, your ultimate goal is to find the value of the ram velocity. Okay, so I'm trying to give you the overall picture. So before I'm jumping into that, like how to get a relationship. Remember, you do need to find a relationship from these three equation 1, 2, and 3. So you gotta need to find a relationship BCY with respect to or function of VR, which I'll be solving it little later. Okay, I'm trying to give you a big picture first, so you can kind of get a motivation why you are finding this three equation, what you are doing with these three equations, right? So let's do that. So energy conservation, kind of seeing it like you are jumping into a little bit difficult stuff slowly at the very end, right? So T1 V1, T2 V2. Anybody remember what is T and V? Kinetic and potential energy. Now kinetic and potential means like the half of mv square and mgh, right? Straightforward. Now when there is a spring, then another potential energy came up. Remember half of kx square? Alan, you remember those? Half of kx square, does it ring a bell? The spring energy. mgh, you remember that for the height itself, right? Half of mv square for velocity. Okay, so those are the things that I'll be doing first. Okay, and then I'll be writing. Okay, first of all, I'll be saying initially there is no movement, so there is no t1, right? Do you know, is there any movement? Both of them start from zero, right? Zero velocity, so the t1 is zero. Again, t is what? Kinetic or potential? Kinetic, right? And what is the equation for kinetic energy? Anyone? Is it half mv square? So if there is no velocity, there is no t, right? Initially, no movement, so no t. So t1 is 0. Everyone got it, right? All right. So what is happening here? When it is at position or location 2, means when the crater is coming to, take a look, always remember that. What is happening? The crater is coming from the top, point A to point B. When it comes to point B, as if like it reaches to the data. Does it make sense? So it doesn't have any more potential energy, does it? It doesn't. Okay, when it is at point A, it does have some height, right? Look at, remember we found the value of the h, right? So we do have the value of this v1, right, initially because of the height. But when it comes to point B, there is no height, so we can say this is 0 as well. But when it is coming to B, point A to B, it does gain some velocity because of the movement, right? Initially, it doesn't have any velocity. So that's why I do keep the T2, which is the velocity is there. That's why I have this T2 is there, right? When it point 2 is referring to at point B, 1 is referring to point A. Does everybody see that? A and B? Everybody see that, right? A and B location? See that, Delina? Okay, perfect. So I'm glad that everybody understand up to this point. So obviously now it will be much easier for me to write the equation. So I have this mgh. You guys remember the value of the h, right? I found it already. And then I have this half of mcbc square plus half of mrbr square. Why do I write both the bc and vr? Because you see, under conservation of energy, both of them are attached together, right? In a sense, like they are moving with each other. So that means one for one block or one crate, the energy that is exerting, the other one need to absorb it, or other one exerting, the other one needs to absorb it. Bottom line, both are together. So if you do energy conservation, you got to count both of them together. Okay. All right. So that's why on the right side you have both half mc square vc square, mc vc square, and mrbr square. All right, so then you gotta just plug all the values, and then here's the catch. So when it comes to BC, now see, if you remember from Pythagorean, can I write VC square is same as like Vx square plus VCy square? Can I write that? I don't remember. So this is like from Pythagorean, right? X and Y component. So all right. So now, if here's the problem now, you started to see the problem now. You have like all sorts of velocities, right? You have like VC, VR, none of that you know. You have some relationship between them, right? Equation 1, 2, 3. You don't know one of them directly, so you are in trouble. In a sense, like you know the H, G, M, and everything you know, right? So you're good on that, but you don't know any of this. So anyone have any idea how to deal with this? Anyone? And by the way, this should be which? This m in the left side should be what? Like mr, mc, or mc plus mr? Only mc. Think this way: the mc or crate is only moving, right? Mr moving up to down. H, that H goes with that mc only, right? Okay, got it. So H goes with mc only, the crate only, right? Because the crate has this height. The roller has this structure fixed, right? Anyway, so it's all right. So now you have this FCR both known, G, H, you know, right? H, you know. So can you find a relationship with BC and VR? Do you have the relationship? We don't have it directly, but we do have relationship with BC with VR. Sorry, BCX with VR. But we know VC has like this VCX and VCY, right? So that means if you're gonna find the relationship with BCY with VR, which we're gonna be finding it from here, then we're good. So see why the problem is difficult? So you have these three equations. From these three equations, you have to find the relationship with BCX with VR, BCY with VR. BCX with VR, we already have it, right? It's straightforward. But the other one is gonna find. So that's why I didn't quite solve this part yet. I'm gonna do it now. You understand? So once I'm gonna solve this part, then I can able to solve it. So you need to know why I'm solving it. That's why I leave it here, okay? So you know what's the motivation to solve it. Otherwise, it will gonna seems like a math that you're doing only. Okay? Got it? This is, by the way, a difficult problem, and take home you'll be expecting a difficult problem in final. Okay, because it's take home only. Okay? And in class, I have never tried to give a difficult problem. If I give a difficult problem, I solve similar one. So you won't be feeling stressed, right? All right. So okay, so let's solve. Okay, so first of all, let me proceed it a little bit further, and then I'm gonna get the relationship for that. So I have this MCGH plus, okay, MCVCX square VCY square plus half of MR VR square. By the way, what's our goal? What is that we are trying to find? You guys remember by now? VR, right? So okay. So now let me go back what I was saying before, right? So I'm gonna do it this way. I'm gonna write it from here. I have these three equations, right? Eliminating BCR from equation 2 and 3. Okay, see, you have this VCR in both equation. Your goal is not to keep it at all because you are seeing it, you don't have a VCR anyway, right? So to eliminate it, what you got to do, this one is method of elimination. You have done this thing all the time in algebra, right? Method of elimination, remember, x plus y equal to something, x minus y equal to something. You find the value of the x and y. How do you do the method of elimination? Exactly same thing. All right. So you have this BCX equal minus VR plus minus BCY. So cos of 30 sine of 30. All right, got it so far? What did I do? I skipped so many steps. Basically, if you have to, you see, delete this VCR, right? So this one, for this one, you got to divide for all of them by cos 30. You understand? You agree? And if you want to delete this one, you got to divide both sides by sine 30, right? So then if we're going to add them up, so these two are going to go away, right? Okay, so like if you have x plus 3y equal 20, 2x minus y equal 5. Can you solve it? X and y. Can you solve it? You have two equations, two unknowns. Can you solve it? We have two equations, three unknowns. We can't solve it, right? But we can definitely take out VCR. Why? We don't need VCR. We have seen it. Don't get it? Focus on this. I have two equations here. Everybody should be able to solve it, right? X and Y equations. That's, I don't know, that's high school. not at this stage. Everybody should be able to solve it, right? Arlene, you have two questions, two unknowns. Everybody should solve it, right? Lorenzo? Two questions, two unknowns. It's very straightforward. Now, what do we have here? We have two questions again, three unknowns. We can solve it, but we can take out this. How? Whatever is with VCR, we're going to divide it, right, in both equations. And then this is you have plus, you have minus, so this is going to cross out if you're going to add them up. If you're going to do that, we're going to finally come. This is a little bit, some steps goes away from there, right? This is the final step. I'm going to keep it as a homework for you, okay? Why don't you be able to come up with that, okay? Let me give you the final form of the equation, okay? So then, I mean, we are about to finish our time. So let me give you the final form of the equation. So you're going to have this VCX is 4 VR. We know that, right? VR is VR. And then you have this VCY. And VCY would be, by the way, so there's another steps down as well. So VCX equal to minus 4 VR. So basically, let me not skip the steps. I know this is confusing to you. So I'm keeping the negative, okay? And then you have this still cos 30. I'm not going to give you the value for that. Sine 30. Okay? Okay, so then VCY, I can rewrite this by 3 sine 30 by cos 30. It won't be taking more than 30 minutes. 2-3 minutes, okay? Just stick here, would be getting the solution. So 8.66 VR. I'm gonna put a box here, even though this is not my final answer, okay? What's my goal here? To find the relationship of VR with VCY, because I do have a relationship with VCX with VR, okay? And then it's very easy. So what I'm gonna do, I'm gonna just start to plug all the values. So I have what? In the left side, I have 10 multiplied 9.81. I'm gonna skip the units for now. So 3.5 sine 30, that's my h, right? And then half of 10, is the 10 kg, right? And this VCX and VCY, I would be writing 4 VR, 8.66 VR. I'll talk more about this problem, don't worry. So I have half of 40 multiplied VR square. And then I'm going to have 98.1 multiplied 3.5 sine 30. Okay, and I have 5 multiplied 16 VR square plus 5 multiplied 8.66 square VR square plus 20 VR square. Okay, so I have 3 VR. So I can rewrite this whole thing 5 multiplied 16 plus 8.66 square plus 20, the whole thing VR square, and I'll be doing the math 171,675. If you get confused, the left side now in right side now in left side. Did you got it? All right. So then this is the last line, okay? So the VR, I think I'm putting everything on record. So please watch it at home. If you are in a hurry or didn't get the class note at the last moment, okay? And if you still have question, I'll be definitely answering you that when we're going to come back on Wednesday. And I'll also review the whole thing again on Wednesday, okay? So there won't be any confusion as well. And the VR value would be 0.601 meter per second, okay? You got it? You guys are now actually able to start homework number 11 because the theory that I covered, restitution, coefficient of restitution, that one needs to be used. And I have some math problem on that. I'm going to do that as well, okay? Again, the goal is by tomorrow, most likely, I'll be trying to finish it. If not, even Friday, I'm going to start chapter 16 for sure, okay? So that's the goal. So to give you a total wrap up, this is a little bit challenging problem. We have the thread and the roller, okay? One is moving in a ramp and an angle, right? X and Y velocity. Another is moving only in X direction, the roller, right? So only X velocity. So once we find the relationship of the velocities by doing the force triangle and everything, then we just use it in energy balance equation, right? For kinetic and potential energy equations, right? And then finally get the value of the VR or the velocity for the ramp. Now, as I said, like, please watch the video lecture again. This part is tricky, how I did that. And focus on this, what I was saying, like, because this is so important for your final exam.